All right, so we know that star formation is associated with filaments of dense gas, and not uniquely, because up there there's some round blobs that have stars in them, but that doesn't really matter. That's the Herschel submillimeter and some protostars from Spitzer. And there are at least two hypotheses for, is this thing right? It's a little higher, okay. Sounds kind of uneven, yeah. All right, no? I'll just hold it, okay. Anyway, there's this theory of gravitational fragmentation, that you form a hydrostatic filament by whatever means, and then you form the cores inside the filament by just the standard gravitational fragmentation. And in this case, these concepts like the critical mass to length ratio and instabilities come into play. And then there's this snow globe star formation theory, and in case people aren't familiar with a snow globe, if you come from a country that doesn't have snow, it's a glass ball with water in it and little white flakes. And what you do is you shake it like this, and then you put it on the table, and you wait for the turbulence to decay, and then gravity takes over, and you get the illusion of snowfall. And in astrophysics, you have your numerical hydrodynamic code, and you put in the turbulence, and then you wait for the turbulence to decay, and gravity dominates, at least locally, if not globally, kind of leading to the illusion that you have a theory of star formation. And in this case, the process is controlled by the inertial forces of the larger scale flow, and the filaments and the cores are just random events. Now, the problem with this theory of gravitational fragmentation of filaments is the timescales don't match. And so this theory really can't be right. The snow globe theory, it's kind of hard to say. I mean, it's certainly right somewhere. The interstellar medium is definitely turbulent. But not all of the filaments and cores in the filaments look like they're random events. So the proposal is to use magnetic filaments to solve this timescale mismatch, so that the filaments can have a longer timescale than their crossing time, and the fragmentation is shorter than the lifetime of the filament. And that way you can create some periodic structures as observed. So the outline of the talk is to review some observations and then show that the magnetic filaments can be in pressure equilibrium, how they might be formed by reconnection, and how they might fragment. Okay, so the filament that is the model filament is this B211 filament here, and that's seen at the red arrow in the C18O observations, and the magnetic field, the large-scale magnetic field is perpendicular to the filament. Right. And on detail, you can see that there's a number of cores that are equally spaced along the filament, plus some additional kinks. Now, these guys, Alvaro Hecar and Mario Tafaya, noticed that the filament contains different velocity structures. So you see that there's one or two spectral lines at different velocities within this. It look like they're part of the same filament. And when they follow these velocity features, they find that this major filament is made up of these sub-filaments, which are coherent in velocity, and it has this kind of braided look to it, right? And let's see. So they propose that this idea that the filaments are formed by the turbulence, and then once you have the filament formed, then you fragment it by gravitational instability. And that hypothesis was also discussed in this review article by Philippe André on Now, this isn't really a good idea because these filaments are kind of long and thin and subsonic, right? So they're about half a parsec by 0.1 parsec with subsonic velocities. So the crossing and the collapse times are very short, but they contain stars that are could be as much as 2 million years, right? And there's lots of these filaments. And the dynamics really don't look like they're dominated by a larger scale turbulent flow because the velocities are too low. And they don't look entirely random. Now, it's quite easy to see that the global collapse of a fragment or a finite cylinder is going to be much faster than the fragmentation time. Because if I have a cylinder, you make an equilibrium cylinder and you cut it into pieces and you let it go, then there's no gravitational force on either end keeping it in balance, and it'll just immediately collapse and try to turn itself into a sphere. So what we're going to do instead is make up some structure like this, which is going to be some sub-filaments within a larger filament, and the magnetic field is going to be running along those green arrows, and then we'll have the, that'll be threaded by these sub-filaments. Now these flux tubes can be in pressure equilibrium if you have you can set up kind of whatever density profile you want by combining the toroidal and longitudinal components of the magnetic field into mix these negative and positive pressures, right? So this gives you a helical magnetic field, right? And so here's 3 different density profiles for different ratios of the toroidal to the longitudinal magnetic field. And the green one in the middle there is just the hydrostatic profile, right? So this, so then you could have flux tubes in pressure equilibrium with a more extended, more uniform, more gas. That's obviously an idealization there, but now you can form the subfilaments in a tearing instability if you have a sheet with opposed fields. We'll get to the size scale in a minute. But alternatively, if you have a uniform field, you can fold it to create regions where the field lines are opposed, and then the reconnection can isolate parts of the field into these flux tubes. Now we have to use Alex Lazarian's and Ethan Vishniak's rapid reconnection to do this, because the timescale for just reconnection is quite long, as Alex was saying about your coffee a while ago, that the limiting factor on the reconnection is the speed at which the gas can flow out of this narrow reconnection region, right? So it can flow out at the Alfvén speed. And then that region is something like the length scale divided by the magnetic Reynolds number. And that number is very big in interstellar medium, something like 10 to the 12 in molecular clouds. So the reconnection time would be about 1 billion years. And then Alex and Ethan proposed that the magnetic field, the turbulence in the magnetic field would essentially speed up the reconnection, replacing the ohmic diffusion with the turbulent diffusion. So this little picture just shows a jet leaking dye into a turbulent field, and with the turbulence, of course, the spread of the dye is very much more rapid. I might think about it a different way. I would say the length scale for regular reconnection is on the electron gyro radius scale, which is kilometers, which isn't really even astronomical unit, and but if you replace that with the with this scale, which is based on the curvature of the turbulence, that's in fact the Taylor microscale, then you can scale up the magnetic Reynolds number by the ratio of those two numbers and bring the reconnection time down to something more reasonable. Okay, now once you've got the filament and it's embedded in this larger scale magnetic field, and the question is, how would you fragment the filament? Because obviously, with the magnetic field would prevent the formation of the standard gravitational instabilities, but you still have these plasma instabilities, particularly these sausage and kink instabilities. Now the timescales for these are just the timescales without the self-gravity. I was working on this dispersion relation, but it got more complicated than I expected, so I didn't finish it. So I just wrote down here these standard ones. Now you can see here you've got a p over rho. That's a derivative of p over rho. So that's something like a sound speed, and that's a pressure scale length and the radius of the cylinder. And the kink instability is kind of moving at the alphane speed. So these are reasonably fast-growing instabilities. So then, if you have a magnetic field, magnetically dominated filament, then it won't collapse because it's tied to the larger scale magnetic field. And so the lifetime of the filament is greater than what it would be hydrodynamically. And you can make these subfilaments in a time scale that's shorter than the lifetime of the main filament. The subfilaments can persist in pressure equilibrium, and they can fragment on a time scale that's shorter than the lifetime of the subfilaments. So the gravitational fragmentation doesn't work too well because the time scales are wrong, and we're not so sure about the theory of turbulent star formation. It's kind of hard to say what's going on with that. But the magnetic filaments seem to show some promise.
Okay, thank you.
I just want to point out that there are recent studies show that there's no need to invoke magnetic effects. That filamentary structure is the most favorable situation to allow the small-scale density perturbations to grow, and which leads to the fragmentation of filaments before the overall contraction of the entire filament overwhelms them.
Eric, is there any reason, we've seen helical filaments, or rather helical fields and filaments a couple of times in this conference, is there any reason to believe that there really would be a helical magnetic field in a filament? I mean, I didn't even know if Fihi and Pudritz actually believe that the helical filaments are even right. And you can fit, especially in observations, you can fit a helical field or a field piercing perpendicular and get the exact same observational signal. So is this a good starting condition?
Apparently, they don't need the speaker. Okay, I think we should. No. Actually, okay. I should give you a chance to answer. Okay. Answer.
Were there any more questions? Or?
No. Okay, in this case, Henrik, ask what you want. Yeah, but quickly.
Well, it was essentially a comment that the timescale mismatch.
Comment. No.
Yeah, well.
Any question?
Well, a question. How do you? Okay. How do you avoid accretion onto the filament that could solve the timescale mismatch? Because if it's accreting from the outside, then you're continuously feeding the filament with more material. So as much as you're forming stars, you can feed it with gas.
Why do we have to avoid accretion? I mean, I'm not sure that's. I think the filament is formed in the turbulent medium, so you require some kind of turbulent and inflow to form the filament, right? And so it's going to be formed where there's some folding of the magnetic field, right, by the larger scale flow. So I'm not sure that's an accretion process, but.
Okay, I think we should thank our speaker. If we want to go to the bunker.